All right, what's going on, you guys? Another LeetCode video today. Today we're doing a video on a problem called task scheduler. So we're basically given an array of CPU tasks, each represented by a capital letter, and then cooldown time in. So we're basically, given that we can complete a task with one interval. However, identical tasks can't be, they have a cooldown, right? So if n is greater than 0, there's going to be some cooldown. So we're basically coming up with a sequence, right, with the minimum number of intervals where we can complete all the tasks, given, all the tasks that there are to do, and then the cooldown. So that might be a little confusing, but let's walk through the problem with whiteboarding to kind of see what's going on here. So the tasks are given, before we go over to the whiteboarding, let's note that the tasks are given just as a vector of characters. So that's the input. It's just a bunch of tasks in a vector, which can have, occur more than once. And then we have this cooldown in. So like after we complete a task, if the cooldown is n is 2, like you can't just take A and then do A again. We've got to wait for 2 intervals before we can do A again, right? So that's what the cooldown is. So yeah, let's look at this problem. So let's say we have the input, this input. Let's just give a couple A's, maybe a B and a C and a D. And then let's just say n equals 2. So we're given this input. Okay, so let's just kind of walk through this and just choose some tasks randomly, right? So let's just choose B first, okay? And then maybe we can choose C, and then maybe we could choose D, and then we'll choose A. Okay, but so we've gotten rid of all of these, we've gotten rid of this, so all there is an A now, but n equals 2, so we've got to wait twice. Okay, and then let's get the A, we've got to wait twice again, and then we can get the A finally. And that'll finish it off. Okay, so how many intervals is that? That's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And notice how much time we're wasting when we choose tasks that occur at a low frequency. When I say frequency, I just mean the number of times a task appears in this vector. So look how much we have to wait when we choose the highest frequency last. So let's see what happens when we choose the highest frequency first. So let's see if I can undo all this. I might have to just go in and erase. Yeah, okay, so this is good. All right, so let's see what happens when we choose the A's first now. So that was 10. We had 10 intervals in the first time. So let's see if we can do better than 10 intervals. So they want the lowest number of intervals. So let's choose an A. Okay, the cooldown is going to be 2, so let's choose a B. Okay, cooldown's still there, so let's choose a C. Okay, but we can choose an A again now, and it occurs at the highest frequency of 2. So we'll choose that other A. So now it's gonna have that cooldown again. So let's just choose the D. There's nothing else we can choose because there's still a cooldown on that A. So let's just we're gonna have to be idle for a second, but then we can choose that last A. So this is way better. When we choose the task that has the highest frequency, this is just a property of scheduling. You want to always choose the task with the highest frequency if you're trying to minimize idle time and there's like a cooldown. So A, B, so 1, 2, 3, 4, 5, 6, 7, 8, right? So that is, wait, 1, 2, 3, 4, 5, 6, 7. That's much better than 10, right? So that's the gist of what I was trying to show here is, we want to choose the task with the highest frequency when there's a cooldown to minimize the idle time. So that's a pretty core property of this problem, just in a nutshell. So how do we do that, right? So there's a couple data structures we could use. We basically want to keep the tasks sorted by their number of frequencies. So the first thing we're going to do when we're solving this is basically just use a hash map, right, to count up frequencies of the tasks. Then we can use a max heap to put all of the tasks in based on their frequency, right? So we're going to have like a max heap down here. Let me make it a little larger. So we're going to have a max heap down here, and we're basically going to put all the tasks in by frequency, right? So A will have a frequency of 3. It'll be at the top of the heap, right? Top of the max heap. We'll have like a B with 1, a C with 1, and a D with 1, somewhere down there under that top value in the max heap. Okay, and then we basically just need to iterate through, where we're incrementing a intervals count, right? We're just going to keep iterating, and we're going to take the top value from a max heap, right? Because that's going to be the task that occurs most frequently. So we would take this A. When we do a task, we obviously subtract its frequency. But how do we handle cooldowns, right? So the way we're going to do that is when a task is on cooldown, we're going to have another data structure. We're going to take it away from the max heap. That way, the next most frequent value will be available next. And then we're going to put it away in a different data structure as long as it's got to cool down, right? So we'll use like a queue, because that just makes sense logically. So we'll use a queue, and so the A will get put at the front of the queue, and it's also going to we're going to store an additional value with it, which is the time at which it's ready. So whatever interval it will be ready to go back basically in the heap. So once this A reaches, this time reaches the current interval's time, we can just put it back in the heap. So, maybe we use this B1, right? There's only one, it occurs with one frequency, right? So when we subtract that frequency, this B just goes away, right? And then whenever this A is ready again, we can simply put it back into the heap. That's going to be and it's not going to have that time with it because it's no longer on cooldown. That's going to be a log in operation, right? Where in is the size of the heap. So that's going to be decently efficient, and then the heap will always basically have the most frequent value on the top of it. So in a nutshell, that's how we're solving the problem. In terms of time and space complexity, we're going to have a heap, right, that has in elements in it potentially. Actually the number of elements that are in the heap is actually going to be limited by, 26 possible tasks that there are, right? So there can only be, it's basically going to be, 20. I mean, you could argue that technically that's like a constant, but 26 is kind of a decent amount. So let's just say, we'll just say that the heap takes, and for the space complexity, big O of n, because also we're going to have that in addition to the heap, we have to have the hash map, right, which is also big O of n. We also have to have our queue, which can also potentially be up to big O of n. So we'll just say big O of n for the space, where n is the number of distinct tasks, and then in terms of the time complexity, that's going to be big O of, if we say n is the number of distinct tasks, it's going to be like n times log n. Log n for inserting and popping from this max heap, right? And then n, because we're going to have to iterate at least through each task. So n is really actually the total number of tasks. Is probably a better way to better assignment for n rather than distinct tasks, because we're obviously going to have an interval for each task, right? So also this cooldown in here we can call m, because potentially if our cooldown, we're gonna have to multiply that variable too, right? Let's just say this is m for the time complexity because I already used n, but if this number is like 100 and we only have like, I don't know, 2 tasks, like that's a good example. Like you're gonna have to be idle like 100 times, so you got to multiply that by the number of tasks, right? So that's got to get factored in. So we'll just say big O of n times log n for the time. And then big O of n for the space. So yeah, let's go ahead and get into the code because there's quite a bit for this problem. So first thing we want to do is let's make a hash map. So in C++, we can do that with unordered map. And this is just going to be like our frequency map because we need to map those frequencies for each task. Like we need to know how many times they occur in that vector, right? So we're just going to loop through that vector. We can say we can use the auto keyword. So for auto task and tasks, every time we see a task, we just need to increment that frequency, right? So that's basically going to count how many times each character task occurs in that vector. So the next thing we want to do is take a max heap and then basically put all of those tasks into the max heap sorted by how many times they occur, right? With the most frequent tasks on the top of the heap. So priority queue, we'll just use, we can use pairs, actually. That's probably the way to go here. So a pair of char ints, right? So the char will obviously be the task, and then the int will just be the frequency. And under the hood, we can use a vector. That'll probably be the fastest. And then, so vector pairs, and then we're also going to need a custom comparator, right? Because we want these sorted by the frequency, and the language doesn't necessarily handle that by default. So let's just go ahead and ensure that comparator is functioning properly by coding it ourselves. So we'll make the comparator as a struct. This is basically just to sort all of the we're basically making this priority queue max heap sorted by frequency, right, with this comparator. So we need it's going to be the operator keyword with this parentheses and then more parentheses, and then we're basically comparing 2 pairs here, right? So those will both be, they can just be by reference. And we're comparing by that integer frequency, right? So, and we want it to be a max heap, right? So for max heap, we're just going to return a dot second less than b dot second. Now, if you wanted this to be a min heap, you would just turn this sign the other way. So yeah, but this is going to basically give us a max heap with our frequency for each task. So we'll just call this max heap, and then we need to put all of those values into the max heap, right? So we're just going to say for auto, we'll say key value in frequency, just for our frequency map, and then so for each one of those key values in the frequency map, we can just say max heap dot push key value dot first, so that's going to be the task, and then key value dot second, that'll be the frequency, right? So all right, so that's that. We also need a queue, right? So one more data structure for when tasks are on cooldown. So that'll just, we'll do tuples, right? Because we need 3 values here in this queue. We need the task, the remaining frequency, and then also the interval at which it's ready to be sent back to the priority queue or the max heap, right? So we'll just call this queue. Let me leave a comment up here because it's a little, there's a lot going on, right? So we have task, frequency remaining, and then the interval, or just we'll say, yeah, interval ready, right? So we also need intervals, right? So let's, we're gonna have an int intervals, that can just be 0. And then we're gonna say while, we're gonna loop, while our, both our max heap and our queue still have tasks in them, right? So while not max heap dot empty, so while that's max heap still has stuff in it, and not let's see, queue dot empty, so and while the queue also has stuff in it, we're going to keep looping. Okay, the first thing we want to do is see if there are any if there's anything in our queue that's on cooldown that can go back into the max heap. So to do that, let's just say we're going to use an if statement here. If max or if queue dot, if not queue dot empty, that's what we want. So if the queue has something in it, then we can take the value off the top of the queue. So we'll say auto, just to do this with easy syntax. You know, I could probably make this code a little shorter, but the syntax would be much harder to read. So with these tuples. So let's just take, we're gonna use this auto, I forget what the term is, but you can take the values from the tuple like this. So we have task remaining, like remaining as in how many times it still occurs, like what the frequency is, and then also interval, right? So the interval that it's going to be ready, and that's going to be equal to queue dot front, right? Whatever's at the front of the queue there, as long as it's, you know, not empty. So now we need another if statement, right? So we need to see if this task is ready. Whatever's at the front of the queue will, you know, you're only putting in one task to the queue at each interval tops, right? So whatever's at the front is for sure going to have the basically, you know, be the close to being done with its cooldown, right? So so we're going to say if interval is equal to intervals, right? So whatever interval we're at, then that means it's basically ready to go back into the max heap, right? So let's say max heap dot push. We're gonna push that's just pairs, right? So we'll push the task and then how many are remaining cooldown or interval variable doesn't matter, right? So and then we just need a pop from the queue. So queue dot pop, and that should handle putting that back into the max heap. So now let's leave some comments because there's going to be a few steps. So put task finished with cooldown back in heap. Okay, the next thing we're going to want to do is actually do a task, right? So we're actually going to want to do a task now. So let's check if first, before we do any tasks, because potentially, you know, all of the tasks in the max heap could be in the queue, right? So with that in mind, we need to check if the max heap actually has stuff in it. So if max heap, and actually let's do this the other way around, that way we don't have to nest any code. Let's just say, let's check if max heap is empty, then we're just gonna continue, right? We still want to increment intervals, right? We want to keep counting up the time stamp that we're at, but we don't want to, you know, actually get rid of any tasks, right? So we're just going to say continue. You know, otherwise, we got to do the next task. So to do so, let's just grab it from the top of the max heap. So we'll say auto because we're going to use this. And actually, let's just get these as their own values. So we'll say int task here is going to be equal to max heap dot top, right? So, and that's going to be dot first, right? And then int remaining is going to be max heap dot top second, right? It's the frequency. Okay, and then frequency, no, second. Okay, yes. All right, so now let's see. So we have the task and the remaining frequency. So there's a couple conditions basically that we're gonna have to deal with. And I'm realizing the syntax for this could be way better. Let's actually just use auto keyword here and then do task and remaining. Same way I destructed the tuple, or broke down the tuple up here. So do task remaining equals max heap dot top. Okay, then we can pop from the top of the max heap. So max heap dot pop, and then we have all the variables we need. Let's just say we've got a decrement remaining, right? So remaining minus minus, and then there's a couple things we want to do, right? So if there are more tasks remaining, like if remaining is greater than 0, then we're gonna have to put this back into the queue, right? To take it, we're gonna have to, not back in the queue, but we're gonna have to take it out of the max heap, put it in the queue while it's on cooldown. But only if the cooldown is greater than 0, right? There's a chance the cooldown is 0, in which case we wouldn't want to put it into the queue, you know, just leave it in the max heap. So, so let's see. So if, so there's a couple things we want to check, right? So if remaining is greater than 0, and the cooldown is greater than 0, then we want to put this into the queue, right? Take it out of the max heap, put it into the queue. So, so the way we're going to do that is we can just say, let's see, we're going to say queue dot push, and then we're going to use this make tuple function to construct the tuple, and then that's just it's going to be, so our values for the queue, remember, are task, so task, the frequency remaining, so, and we already decremented our remaining, so we can just put that straight in. And then the interval at which it's going to be ready, which will just be intervals plus the cooldown, so whatever the current interval is, plus how many rounds it takes for cooldown, plus 1, since we're incrementing intervals at the very end of this loop. So that's pretty much it there. There's one more condition, right? So if there is no cooldown, we just want to put this back into the heap, right? So else if there's still some remaining, so if remaining is greater than 0, but there's no cooldown, we can just put this back into the heap. So max heap dot push on, let's see, it's going to be, just to make the pair, it'll be task and remaining. Okay. And at the end of this, we just want to update intervals, right? So by incrementing it, so intervals plus plus, and then we can just return intervals. That'll be guaranteed to give us the lowest, you know, the minimum possible number of intervals given these tasks. So let's go ahead and submit this. So much code here, wouldn't be surprised if there's a bug, but yeah, let's see. So no matching function for call to make tuple. So this should be a function. Let's see. Okay, I see what I did wrong here. The curly brace syntax is incorrect. They just want the arguments directly. So that should be good though. Should be it. Yeah, so hopefully this video helped you understand this problem better. Let's see, so this one's called task scheduler. So hopefully it helped you understand, you know, max heaps better, and, you know, how to use these data structures and just properties of CPU scheduling in general. So yeah, hopefully it helped. If it did, leave a like and subscribe. See you guys in the next video. Peace.